functions called Euler's integrals. They are widely used in mathematics and physics. It was once discovered that they describe properties of elementary particles in the string theory. Now, it is not our goal to clarify what are these structures for. Our task for now is to figure out what they really are, define their key properties, and learn how to use these properties for solving problems. We're going to show how these functions can be used to the simplified evaluation of complicated integrals. To begin with, there is Euler's integral of the first kind, which is also known as beta function, and it goes like this. Beta of p and q equals integral from 0 to 1. 0 was somehow missing. Of x taken to the p minus 1 times 1 minus x to the q minus 1 dx. P and q are parameters here. If p is less than 1 and q is less than 1, then this is an improper integral, meaning that it has singularity points. Let's see. If p and q are less than 1, then these powers we have next to x and 1 minus x become negative numbers, which is exactly the same as if we had these two factors in the denominator. So if either of them equals 0, the whole function approaches infinity. But we won't be dealing with them. Now let's consider an expression we have under the integral. It may look too complicated on the face of it, but what we actually have there is a product of two simple polynomials, x taken to the p minus 1 and 1 minus x taken to the q minus 1. Let's discuss them. So the first factor is x raised to p minus 1. The limits of integration are 0 to 1. So it is obvious that within this integral, this first factor is a positive number, since x only takes positive values. Now let's pick a few integer values for the p parameter and graph these curves. So for p equals 2, we'll have simply x. If p equals 3, we'll have x squared. If p equals 4, we'll have x cubed. Now let's graph these curves. So what we have is a straight line, a parabola, and a cubic function. And here we go. A straight line, a parabola, and a cubic function. We may notice that no matter what value p parameter takes, integer or fractional, these curves will still pass through the points with the coordinates 0, 0, and 1, 1, which is quite natural. Let's see. If we substitute 0 and 1, we'll have 0 raised to p minus 1, which obviously equals 0, or 1 raised to p minus 1, which is equal to 1. Now let's move on to the second factor. The limits of integration are the same, 0 to 1. And we can see that the second factor is also a positive number within this given interval, since x never exceeds 1, and an expression within the brackets remains positive. Now let's pick a few integer values for q parameter and graph these curves. So for q equals 2, we'll have 1 minus x. For q equals 3, we'll have 1 minus x squared. For q equals 4, we'll have 1 minus x cubed. And again, what we have is a straight line, a parabola, and a cubic function. Let's graph them. So we have a straight line. case, these curves still pass through the points with the coordinates 1, 0 and 0, 1. So for x equal to 0, we'll have 1 minus 0 raised to the power of q minus 1, which is equal to 1 raised to q minus 1, which equals 1. And for x equal to 1, we'll have 1 minus 1 to the q minus 1, which equals 0 to the q minus 1, which equals 0. So we may say that the second factor gives us curves of the same shape as the first one does, only decreasing and shifted by 1 to the right. Finally, it turns out that under the integral we have a new curve of some kind, and we were asked to find the area formed by this new curve and the x-axis within the given interval. Now let's try and picture this area. Suppose p equals 2 and q equals 3. This way we'll have beta function of 2 and 3, which is equal to the integral from 0 to 1 of x multiplied by 1 minus x squared dx. So we have a straight line multiplied by a parabola under the integral. Let's graph these two curves. A straight line is already here. Now we need to graph a parabola. And now we'll start multiplying values of these two functions for each x moving from 0 to 1. And thus obtain a graph of this new curve we have under the integral. And the area between this curve and the x-axis is the one we were asked about. Now let's switch values of p and q in the formula and see what happens then. So this time we'll have p equal to 3 and q equal to 2. So we'll have beta function of 3 and 2, which is equal to the integral from 0 to 1 of x squared times 1 minus x dx. And again, we have a parabola multiplied by a straight line. So let's grab these two curves. And again, we have a straight line already graphed, and we need to graph the parabola. And then we start multiplying values of these two functions for each x moving from 0 towards 1 and obtain a graph of this new curve. And the area between this curve and the x-axis is the one we need. If we look closely at these two graphs, it may come to mind that it's basically the same old soup just reheated. And it's true. And it occurs that switching p and q, switching values of p and q in the formula for beta function never actually affects the value of beta function. Now let's try and prove that. Let's make a substitution 1 minus x equals t. So we'll have x equals 1 minus t, and dx equals negative dt. We also need to change the limits of integration. So if x equals 0, t equals 1, and if x equals 1, t equals 0. Now let's put this new variable into an expression for beta function. And so we obtain integral from 1 to 0 of 1 minus t to the power of p minus 1 times t to the power of q minus 1 negative dt, which is equal to integral from 0 to 1 of t to the power of q minus 1 times 1 minus t to the power of p minus 1 dt. You may notice that minus next to dt is gone, but I've also switched the limits of integration. And what we have obtained is nothing else than beta function of q and p. So once more, switching values of p and q parameters into in the formula of beta function doesn't affect the value of beta function. This property is called property of symmetry. Now let's consider another important property of beta function. And for that, let's consider beta function of p and q plus 1. So we're considering beta function with one of its parameters increased. And it is equal to integral from 0 to 1 of x taken to the power of p minus 1 times 1 minus x to the power of q plus 1 and minus 1 dx, which equals integral from 0 to 1 of x to the power of p minus 1 times 1 minus x to the power of q dx. Now let's evaluate this integral using the rule of integration by parts. So we'll denote u as 1 minus x to the q, and therefore du equals negative q times 1 minus x to the power of q minus 1. V dv equals x to the p minus 1 dx, and v equals x to the p over p. Now according to the rule, we'd go u times v, so we have x to the p over p times 1 minus x to the q from 0 to 1 minus integral from 0 to 1 of du times v. Now we can pull q over p out front, so we'll have q over p multiplied by this integral, and then we have this minus over here, which multiplied by this minus gives us plus. So we have plus q over p times integral from 0 to 1 of x to the p times 1 minus x to the q minus 1 dx. Now let's see, if we substitute 1 into this expression, we'll obtain 0, as 1 minus 1 over here gives us 0. Then if we substitute 0 into this expression, we'll still obtain 0. So we'll have 0 minus 0, which equals 0, and so this summand equals 0, and we only need to evaluate the second integral. And keeping in mind that x to the p may be presented as x to the p minus 1 minus x to the p minus 1 times 1 minus x, And substituting this into this integral, we'll obtain the following. We'll obtain q over p times the integral from 0 to 1 of x to the p minus 1 minus x to the p minus 1 times 1 minus x times 1 minus x to the q minus 1 dx. Now we know that integral of a difference is equal to the difference of two integrals, so we may have it written down as follows. Q over p times integral from 0 to 1 of x to the p minus 1 times 1 minus x to the q minus 1 dx minus integral from 0 to 1 of x to the p minus 1 times 1 minus x times 1 minus x to the q minus 1 dx. Now if we look closely at this first integral, we'll see that it's nothing else than beta function itself. So we have q over p multiplied by beta function of p and q minus this second integral, which is integral from 0 to 1 of x to the p minus 1 times 1 minus x to the q dx. Now, if we look carefully at the second integral, we'll notice that it's nothing else than beta function we've started with. So what we've obtained is q over p times beta of p and q minus beta of p and q plus 1. So we have beta of p and q plus 1 equals q over p times beta of p and q minus q over p times beta of p and q plus 1. Beta of p and q plus 1 times 1 plus q over p equals q over p times beta of p and q. Beta of p and q plus 1 equals p over p plus q times q over p times beta of p and q. These factors cancel out. And so we obtain q over p plus q times beta of p and q. And that's it. So we obtain beta of p and q plus 1 equals q over p plus q times beta of p and q. Similarly, the following formulas may be obtained. Beta of p plus 1 and q equals p over p plus q times beta of p and q. And then beta of p and q equals p minus 1 over p plus q minus 1 times beta of p minus 1 and q, and then beta of p and q equals q minus 1 over p plus q minus 1 times beta of p and q minus 1. Now let's take a look. As we can see, beta function with one of its parameters increased or decreased is proportional to the initial one. Then, if we look at the formulas we have on our left, we'll notice that beta function with one of its parameters increased is less than the initial beta function, since the coefficient standing next to it is obviously less than 1. Which is no surprise. Let's recall an example we had earlier. And we had this case where p was equal to 3 and q was equal to 2. So we had beta function of 3 and 2, which was equal to integral from 0 to 1 of x squared times 1 minus x dx. And so this was the case where we multiplied a parabola by a straight line. So we had a parabola, and we multiplied it by a straight line. And the product curve went like this. And this was the area we needed to find. Now, if we increase one of these parameters by 1, I say let's increase q, we'll have p equal to 3 and q equal to 3, and this time we'll have beta function of 3 and 3 equal to the integral from 0 to 1 of x squared times 1 minus x squared dx. So this time we're multiplying two parabolas, and one is already there, and here goes another one. Something parabola-like, let's see. Let's make it blue. Let's make it blue. I ruined the whole picture. This was my first parabola. This was my straight line. As straight as it could possibly be. And here's my new parabola. And my new product curve will obviously go below the previous one, since we're now multiplying two parabolas. And naturally, the area between this new curve and the x-axis will be less than the area between the previous curve and the x-axis. Moving on. If p and q are integers, say if p equals m and q equals n, where m and n are integers, we may rewrite, say, this formula like this. Beta of m and n equals, I'd better go with this one. So I'm rewriting it as follows. Beta of m and n equals n minus 1 over m plus n minus 1 times beta of m and n minus 1. Now if we apply it, we'll have n minus 1 over m plus n minus 1 times n minus 2 over m plus n minus 2 times beta of m and n minus 2. If we apply this formula consequently, we'll obtain the following. N minus 1 times n minus 2 times times 2 and times 1 over m plus n minus 1 times m plus n minus 2 times m plus 1 times beta of m and 1. Now we can evaluate this beta of m and 1 function, but I'm going to need some more space. Okay, so according to the formula, beta of m and 1 equals integral from 0 to 1 of x to the p minus 1, but p equals m, so I have x to the m minus 1 times 1 minus x to the q minus 1, but q equals n and n equals 1 in this particular case, so we have 1 minus x to the power of 1 minus 1, which is 0 dx. Do I need these? No, I don't think so. Okay, so I have integral from 0 to 1 of x to the m minus 1 dx, which is equal to x to the m over m from 0 to 1, which is equal to 1 over m. Now if we substitute this result into this formula, we'll obtain this multiplied by 1 over m. And now let's take a look. What we have in the numerator is nothing else than n minus 1 factorial. It may come to mind that it would be really nice if we could make a nice factorial out of an expression we have in denominator as well. But we're missing some stuff to do that, and namely minus 1, m minus 2, and so on until we've reached 1. But in order not to change the whole fraction, we must multiply the numerator by the exactly same number. So we'd multiply the numerator by m minus 1, m minus 2, and so on until we've reached 1. But this is nothing else than m minus 1 factorial, this red stuff. So what we'll obtain is n minus 1 factorial times m minus 1 factorial over m plus n minus 1 factorial. Let me write it one more time. So another property we've discussed is that beta function of two integers m and n equals n minus 1 factorial, m minus 1 factorial over m plus n minus 1 factorial. And these are the main properties of beta function. The next piece will be dedicated to gamma function and its properties. Enjoy!